Okay, today we're going to have a look at the complex roots of unity. So, the fundamental theorem of algebra tells us that every polynomial of degree n has exactly n solutions. Now, this is very important. So, the complex roots of unity are the roots of the equation z to the power of n is equal to 1. Now, in the real numbers, there's only one possible answer, 1. But in the case of the fundamental theorem of algebra, there should be 6 solutions, so 1 and 5 other solutions. So, example 1 says, determine the cube roots of unity. In other words, determine the solutions to the equation z to the power of 3 equals 1. Now, if we do that, we've got z minus 1, or z equals 0. So z minus 1, z cubed minus 1 is 0. So z minus 1, z squared plus z plus 1 equals 0, which means here z is equal to 1. But if we use the quadratic formula, we get z is minus 1 plus or minus root 3i over 2. And that's the answer, right, to those questions. We've just found the solutions of the cube root of unity. Now, it did actually want us to plot them on the Argand diagram, so we might note that z is 1, the argument of z is 0, and the modulus of z is 1. And this one here, if we look at minus 1 on 2 plus root 3i on 2, well, the modulus of that is actually going to give you 1. And the argument will actually give you 10 inverse of root 3 on 2 on a half, which is 10 inverse of root 3, which is pi on a 3. And if we just quickly draw a graph, well, that's going to look like this. So that's pi on 3, which makes this 2 pi on 3. So the argument of this is 2 pi on 3. And if we've got z is equal to minus 1 minus root 3 all over 2, root 3 on 2i, well, the modulus of that again is 1. And if we draw a diagram, that's going to go down here. And same thing, it's going to be 10 inverse of root 3 on 2 over a half, which makes that pi on 3. But that there is pi, so it makes the argument 4 pi on 3. Pi plus pi on 3 is 4 pi on 3. So if we were to graph these, we would say, right, well, all of them had a modulus of 1, so we're actually going to draw a unit circle. In fact, all of the roots of unity will have the same modulus. We've got the first one over here, this is z1, it's equal to 1. The other one was over here at 2 pi on 3, we might call it z2. And the final one was down here, z3. And there we've just plotted the cube roots of unity. But did we notice anything about these roots? They all have a modulus of 1, and hence line a circle with centre 0 and radius 1. And they're all separated by an angle of 2 pi on 3. Now, these properties are crucial and are going to assist us in finding complex roots. So the complex roots of the equation, z to the power of n is equal to r, are defined by the following properties. They all have a modulus of the nth root of r, and they will all be separated by an angle of 2k pi on n. And we're going to look about what that means in a second. Now, whenever we're solving an equation that's not equal to 1, for example, z is 64, z to the 6, then we're finding the 6 roots of 64, not the complex roots of unity. We only use this saying when the equation is equal to 1. So find the 6 roots of minus 64. So in other words, we're finding the solutions to this equation here. Now we're going to use the trick that I just taught you. We're not going to try and factorize this, which would take us a long time. What we're going to do, and this works every single time, is the first thing we're going to do is ask ourselves, the number 64, or negative 64, is over here. It's negative 64. And that has an argument. The argument of negative 64 is equal to pi. And we're actually going to say, first of all, well, r, which we're going to say is like the radius of the circle the complex roots of unity are, is going to be the 6th root of 64. And the 6 roots of 64 is 2. Don't worry about the negative at the moment, just the 6th root of 64 is 2. And then we're going to say, well, 6 theta, because we know we're going to have 6 solutions, so we're going to say 6 theta, and they're all going to be separated by this same value. So we can say 6 theta is equal to the argument of negative 64 plus 2k pi. And if we divide everything by 6, we get our solutions are separated by this relationship here. And we're going to say that k belongs to the positive integers. In other words, it's 0, well 0 is not a positive integer, but apart from 0, we've got 0, 1, 2, 3, 4, and 5. And that is 1, 2, 3, 4, 5, 6 solutions. So if we go, okay, well that means theta is going to be pi on 6 when k is 0. And then pi on 6 plus 2 times 1, pi on 6 is pi on 2. And then we have k is 2, 5 pi on 6, 7 pi on 6, 3 pi on 2, and 11 pi on 6. So the 6th root of negative 64 is our modulus, cis pi on 6, 2 cis pi on 2, which is 2i, 2 cis 5 pi on 6, and so on. Please, in an exam, write all of the solutions. Okay, in our last example, we're going to find the 4th roots of 1 plus root 3i. In other words, we're going to solve the equation z to the power of 4 equals 1 plus root 3i. Now what we need to do is to convert this into modulus argument form. We technically did that up here. We said that this was the same as 1, or 64 cis of pi. That's actually what we were doing. And if we do this, if you convert this into mod arg form, you're actually going to get 2 cis pi on 3. So the first thing we're going to do is take the 4th root, the radius of the solutions is the 4th root of 2. And we're going to next say, okay, well that means 4 theta is going to be the argument of the original 1 plus root 3i plus 2k pi, which means theta is pi on 12 plus k pi on 2, 2k pi on 4. And if we figure out what all of those are, for k's 1, 2, and 3, and 0, we get pi on 12, 7 pi on 12, 13 pi on 12, and 19 pi on 12. So therefore the solutions are the 4th root of 2 cis of pi on 12, 4th root of 2 cis of 7 pi on 12, the 4th root of 2 cis of 13 pi on 12, and the 4th root of 2 cis of 19 pi on 12. And that's the answers. Alright, thanks for watching.